draft physics video. I think we'll play a couple of different clips from a few different videos. Just get a feel for this argument between what's real science and what is, in Piro's words, let's say street science or natural philosophy or some sort of offhanded representation of the description, the modeling of a circumstance, a phenomenon. So in this circumstance, it's a description of the causes that create the effects that we exist in this world, and what are well-reasoned or well-thought-out models of that reality. My argument is that the conventional thinking, the I'm trying to think of some way of combining the words like hierarchy and literacy and authority into some sort of mechanism of a steamroller of a kind of thought ideology, where it's more of the reputation, more of science by reputation than science by argumentation, detail, careful instruction, and accountability, a willingness to have your argument tested. So in the sense of somebody who doesn't wish to be very accountable, this guy Ken Wheeler brings up points about problems, structural problems with notions of how physics is describing reality. The irony is his critique is in the exact opposite direction of my critique, where I believe they have a wave obsession. This guy basically thinks everything is a wave. There's no particle to the duality, it's just wave. And in my opinion, the idea of a medium doesn't work unless it's an active medium, and his medium isn't an active medium. It isn't made of force, and so it won't work as a model. And I think that's been just demonstrated over time. But anyway, he is useful for some purposes, and so he does have a single slit example here that's worth playing.
Now use the black background for contrast. Let me see if I can get better contrast by turning the lights off.
Yes, and then once you get rid of the filter, it gets even better.
Single slit for this. The notion of wave particle duality and the double slit experiment is bogus. What people don't realize is why does light actually bend around the corner? Well,
it doesn't bend, so he thinks it does, because he thinks it's a wave and it curls and it has tension and it has friction. And waves, light doesn't do that. Light never bends. Light enters material bodies, electrons primarily, and is readmitted in a new direction. And that's the only way light changes its course.
Explain that in the second video. Now let me lift up the black contrast card here. What I'm actually doing now, here you can see it really well.
Okay, so this is single slit interference, and you can see no one goes to the trouble to actually count how many bars there are, and how strong or weak signals are depending on what you use for the impediment material, and it does seem like it varies depending on what you use as an obstruction, and of course the width of that slit. But theoretically this would be a standard. You could go to a certain width and you'll get a complete pattern, and then the pattern will just turn into a dot because you'll lose the interaction that's creating these diffractions. So as you go wider and wider, the diffractions will get weaker and weaker and fade out. And then as you get narrower and narrower, this center part will just get stronger and stronger and just dominate the entire field. And the number of photons will diminish at the same time. But clearly a very, very strong pattern. Alright, and let's contrast that against this Yale professor. So we'll go back here, or so. And this is his representation of the two-slit experiment. Now, he won't be mentioning Huygens, because it's two slits. And Huygens is the idea of the infinite number of wavelets creating the next wavefront, all of that. Because in the 2-slit experiment, it would create a complication, because then it would end up being the 4-slit experiment. This should increase the amount of interference being created. So they use a fake contrivance to create 2 waves in a single slit, and then they don't use that contrivance in the double slit, because they know the contrivance is a contrivance. You can't use it everywhere, because if you use it everywhere, you'll break the math. And the math doesn't account for this effect here in the double slit experiment, where the signal breaks off to nothing and then starts up again. And so this is just the single slit. Has obviously a lot of character, as long as the slit width is wide enough.
One slit open. And if I move that observation point, I get some pattern, pretty dull, looking like that, and I'm going to call it I1. That's the count.
Right, so he's doing the typical Feynman thing. There's 2 open slits. If I block one of the slits, then the light only goes through the 1 slit, and this is the pattern I get, just a blob. And the other problem with this whole thing is the way he's drawn it, with these proportions. He's almost implying that, this is a tiny, tiny speck of a distance. And on this range, it would be this tiny, tiny little speck here. There's no reason to think that the light that would go straight through would go anywhere else but that very center, even if it was a little tiny bit off. And so it's a kind of a gross distortion in the sense that the proportions are just so out of proportion in terms of the distances involved. This is many meters across, this is nanometers. And so obviously anything that's going a little tiny bit straight, but not quite straight, is going to end up being just in here, this little tiny space here. But anyway, that's the point is you see it. You just do it as a blob, and he'll do some more of that.
Function of position up and down the wall of detectors. Then I repeat the experiment with this guy closed and that guy open, and I get another count. Looks like that.
Okay, so this is what we already, like I said, this is known in Newton's time, that you had no expectation that you'd get a cone. The rational expectation, if you're a physicist and you know physics, the rational expectation is that you're going to get Newton's rings, and that's all this represents. When you turn into a slit experiment, all you're really doing is cutting off the circles, but this is just Newton's rings. So Newton already knew about this. A tiny aperture creating rings of light and dark when you have monochromatic light. Like I said, the effect is much more diminished when the light is able to, when the blues, the reds, and the yellows don't line up. Then it gets a lot blurrier and you have a lot less of a pattern to deal with. It's still there, but it's less apparent. But it's Newton's rings. So, but this is how quantum mechanics is being taught. And for somebody to say that, to call my physics street physics, and to say this is Yale and this is real physics, when this is how you treat reality in this superficial, inaccurate misrepresentation of the truth, because it defends a story you're going to tell about the incomprehensibility. Now, I could go back in this video and he'll explain how quantum mechanics doesn't make any sense. Well, here, I'll play some of it. What the hell?
Ron, you will feel it in only one tiny region, one spot.
Sorry.
Electron dumps all its charge, all its momentum, all its energy to one little part of your face.
So he's talking about electrons being particles, and likewise photons, in the sense that they always interact in the world in this conservational manner, and that their end effect is always in one location. So whatever they make up to be the causes of the effect, the causes have no material provable reality, and the effect is very particle-like in that the impact is complete and not partial.
So there's nothing wave-like about that. It's not like getting hit by a boxing glove, which can hit your whole face. Electron hits one dot. Okay? Or if it's an electron detecting screen, only one pixel is hit by the electron. And into that pixel, is given all the charge, all the momentum, all the energy of that electron. That's exactly what particles do. So when you encounter an electron, it is simply a particle.
All right, now the idea of turning it into a particle is again not recognizing that the nature of it is not particulate. It's a machine. Electrons do kind of sophisticated things. They absorb and emit photons. They're just not they're not like a solid body, because they're doing something a little more complicated. And so again, it's the idea of calling it a particle is okay in the sense that it's a collection confined in space. But it's like calling us a cell. You know, we're made of cells. We're not a cell.
So where does the problem come in? Where does the quantum mechanics come in? It comes in when you do the famous double slit experiment. That's the key.
So, you know, just to highlight, again, people who dismiss this as being an important argument, he's acknowledging that this is a key experiment, and yet they don't take it very seriously. They don't take being explicitly accurate very seriously. And in a sense, they misrepresent the truth in a rather dramatic way, in the sense that they have principles that don't apply evenly, and in the sense that they describe circumstances that aren't the reality.
The entire quantum mystery is in the double slit. Part of the resolution is in the double slit, but the rest are a little more difficult, and I'll try to tell you. First, I want to tell you what goes wrong with Newtonian mechanics. After all, if everything is a particle, what's the big deal? What's the problem? The double slit experiment is a problem. That's what puts the nail on the coffin for Newtonian physics.
Okay, so that's his argument. I think I've played this before. Well, they all say the same line. I think the guy from MIT says exactly the same thing, that this is somehow the nail in the coffin. And clearly it's single slit diffraction. If anything is a nail, that's the nail. And my argument is that obviously it's not a nail when they had to come up with a wacky contrivance that includes infinities to try to rationalize an explanation that involves waves. And they're forcing it to involve waves. They're trying to make waves make sense when it doesn't happen in water waves, and it's not wave mechanics. It's an on-off pattern. And on-off patterns can be created by a lot of things. It's like every sound you hear that goes chung 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 chung. Are you to say that every time you hear those sounds, that means it's an engine? Nothing else can make that sound? Nothing else goes chung 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 chung. Just engines? You know, a clock tick sound, tick 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 tick. My wall does that sometimes. You know, from the stress of the wood popping. You know, it'll go tick 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 tick, quite reliably, almost like a clock. Does that mean my wall is telling time? That it has a flywheel in it? No, it doesn't.
And here it is in basic version.
Alright, well, I didn't get all the way back to the part where he fucked it up. So anyway, but you get the idea. So he's going to do the classical, you get two blobs, and then when you open both slits, you get on, off, on, off, on, off, and obviously didn't draw it to much in a decent scale. And it's just very, very sloppy, would be my argument. Treatment, and to call somebody street in an environment where the professionals are taking so little care to properly represent the truth is kind of an amazing statement. Alright, so we'll jump to this video, which is a representation of an experiment done where they move a mask across the two-slit experiment. Now, the unfortunate fact is, what I found out in researching this experiment, the images are good. They're good for my purposes as much as they are for any wave particle theorist. The interesting thing is that this is sort of a misrepresentation, because this experiment was done with electrons, and then they converted the electrons, they put them through an electron multiplier, and then turned them into photons. So they displayed a representation of the electrons collected amplified that signal and then projected it as photons, which, in my opinion, there's a little too much processing for one to argue that this is a best representation of reality. As you can see, now as the target moves over, so now you have one slit open, one slit closed. And there's obviously quite a bit of leakage here, but you see very strong fringes for the one side, so that means one side is producing its portion of the signal, and then you have some indication of the other side, and you have this blob in the middle. Now this is where the problem comes in, because this is electrons. There's not like an iris setting, where you can open or close the iris depending on how much light is coming through, so you don't flare the image. And so this image can get flared because it's at the wrong exposure. So if the exposure doesn't change with the intensity of the light, then you're going to not get the same resolution. And you can't really do that with electrons. So unless they were willing to process the electron information and clean it, they wouldn't have proper exposure to be able to get detail at any exposure. So what you can sort of see is that this is a line of white, and which hard to tell when there's kind of an optical illusion, but what's really going to happen as this progresses to the double slit is the only thing that really is going to happen is these little top parts will be these little lumps will rise up. It's not like it's going to get more resolute. It's just that they're going to rise out of this thing. So it's not like white spaces are going to become dark. It's more like, this is going to get thicker. So there you have the two slits fully open. And I guess I would argue that if I took that single, the previous images, they would still fit right inside here. So that's sort of an optical illusion, that if I take these little lumps off, it's the same blob that's in there. So the only thing that was really added by having the two slits complete is these little top humps were added. And also the argument would be is that they have this filter going on the outside of the slits. They really should be on the inside, preventing the light from getting into the slit, because theoretically it probably still wouldn't matter. By my theory, the interaction's happening inside the slits because of the field energy in the slits themselves, and that isn't going to be affected by anything you put in front or behind. So the mixing of the electrical potentials, if you want to call them that, the mixing of the electrical potentials by the middle impediment has already taken place. And so you can see now it's closing the other slit. And the thing is, when you look at, I'll probably do that someday, let's go to the Google page, you can actually see all of these images as static images. And when you see them, it's kind of funny, because when one slit is covered, you get a slightly different, more pattern than when another slit is open, which is a little unusual also. But you can see, strong pattern. It's all still here. And these are just, you can just have the vague sense of the humps still being there. And then you go to the nothing. But even at both slits covered, there's enough leakage for you to still have quite a bit of signal. Alright, so I don't know what it proves or disproves. It's just an interesting experiment, but unfortunately, like I said, I didn't realize how much, there's a lot more to that experiment than what is presented, in the sense that it was done with electrons. It'd be better to do it with photons, get stronger bars, and then see what how the photons are, how those strong bars are affected. Alright, this 60 signals video was interesting because it was mostly about electrons, so I'll play some of this. I think there's going to be an ad, unfortunately, but it's got to load eventually. Come on, YouTube.
So what we have here is a ball, and you imagine if I take this ball and bounce it off the table, it'll bounce off that table, and if I do that exactly the same way each time, then what will happen is that it'll hit the same point on the wall. Imagine if we had 1,000,000 balls, we could control it so that each and every one of them hit the table in exactly the same way, exactly the same velocity. They'd bounce off, and we'd end up with a very well-defined...
Okay, his argument further in here is that these balls, electrons, will bounce off the same surface, be thrown in the same way, and they'll end up creating a bar pattern here, an interference pattern, which is sort of interesting because it's the no-slit experiment, essentially. And it's sort of implying that somehow electrons bounce off tables and everything's static and the same every time. And that's not what electrons do. It's not what photons do. They don't bounce off of things. They get absorbed into things and then get readmitted. They cycle into something and then cycle out of something. They do U-turns. They don't bounce. They U-turn. And there's a big difference. And it's a difference in conception. They're assuming that everything's a hard body and that everything is doing some sort of, in a sense, a kinetic thing with these big, giant, massive particles that aren't, as I pointed out, that aren't really particles. They're complex machines, and those complex machines go into a complex field, and that they just sort of bounce right straight back. And that's not what they're doing.
dent in the wall.
Okay.
Alright, so let's go forward a little bit. This guy with the funny hair is funny. Yeah.
Enormously important for chemists.
So now,
Okay, so electrons are important to chemists and blah blah blah. So here, let's go through this. We'll play a little bit of this part.
why do electrons behave so differently from little balls? And maybe that's because, well, actually they're not little balls. There's something different from little balls. What could that be? Well, let's go down to the lab and we'll see another experiment whereby we see these patterns, and maybe the patterns we see in that experiment will help us to understand really what these electrons.
Okay, so it's not the two-slit experiment, so it's not what you think. So let me play some more of this guy.
An electron is something, a negative charge, that can be transferred between one atom and another, rather like changing money. But on the other hand, if you want to understand the structure of the atom, then you have to treat the electron as a wave.
Yeah, well, you really don't. But so the idea would be, too, is just to understand, if an electron is over here, you're going to exchange it like money. The point is, when you send it, the force of the send is now part of the electron. So the electron isn't the same electron that was here, this static electron, because now you're sending, and it has sending energy inside of it. And so when it arrives in this new location, the sending energy is what's extracted from the electron. And that sending energy can make the atom move, or that can make it emit another electron, or it can make it emit some photons. But the sending energy changes the electron. An electron moving is different than an electron not moving. A human being that has velocity is different than a human being that doesn't have velocity. Your parts are different. Your nuclear energy is in a different state.
Hello, George. What we have...
This unnecessary hello Georging part. So this is an experiment. Well, we'll just play some of this, but it's not terribly interesting. We'll do it.
A light bulb is that in the laser, the photons of light all come out in step. So we've got an obstacle through which those photons, those little packets of light, have got to pass. And so if you follow this through, you follow the path of light, down here we have the light, and instead of it all piling...
There, so now you can see the double slit. So this is a double slit experiment. And you can see the dead here. This and this is not part of the mathematics. So that you can see the pattern, then nothing, then pattern, then nothing, then pattern. And the number of dots here you can see is not that many. 1, 2, 3, 4, 5, 6, 7. Just 7. And the center dot isn't on the center. Here's a center line, presumably, and the center is right between the two dots. So there's actually a dead space in the center in the double slit experiment. And this would be 1, and this would be 1, and then this would be 2, and this would be 2, and this would be 3, and this would be 3. So that's a difference in the math, as in how you count from the center. Well, that doesn't even work because 7 is the this is the center one here. Sorry. Okay. Center is here, so it's off their line. And you have 3 on either side of the center. That would be 7, Gary. But those are important numbers, and they're not part of any description of the 2-slit experiment. Nobody analyzes this number of dots and finds it at all interesting or curious. And this is, in my opinion, hard evidence of what's really taking place, which is the number of field lines. So if I start cramming the slits together, these dots will start merging, and you'll end up with just 1 dot eventually.
No, what we see is this pattern exactly like that I was discussing in terms of the electrons. And this is something called the double slit experiment. We have 2 slits here.
No description of Huygens in this creation of an interference pattern.
The key thing here is that what we have is light. Light is a wave. That wave...
See, he says it's a wave. It's as if that's all I got to say is it's a wave, it's a wave, it's a wave. No, it's a frequency of cannonballs.
It's coming through, and it's interfering constructively, destructively.
And that's your assumption, but again, those are just assumptions. And it's not doing any of this. What it's doing is going through one slit or the other, and it's being diffracted at a specific angle depending on what it travels through in terms of the tight material slit. So around all material objects there is a field of electrons, and the photons are hitting that field of electrons, and they're being diffracted, they're being turned in their course by the electrons.
To form this type of pattern. The key thing here is related to how those waves interfere with each other. But we see exactly the same pattern in terms of this, these bright spots, these dark spots, when we do this experiment with electrons. And that leads us to...
Now, it's not exactly the same pattern, so again, that's another exaggeration. It's a little harder to do with electrons, and the signal you get is a lot sloppier. And I would argue it's a lot sloppier because now you're crashing electrons into electrons. And sometimes that'll produce not exactly the same kind of geometry. I will play a little of this guy.
That, unless people are very good mathematicians, and I'm not, it's not very clear what the equations mean.
Everyday common sense does not allow us to describe it in simple words. The concepts are too elusive and slippery for the English language, but it has these particle-like qualities which it always takes with it, such as its mass, its momentum.
Now, some people would argue that photons don't have mass, but clearly Einstein would have argued they do, because they couldn't have been bent by force if it wasn't for that mass. But the truth is, they don't have material mass. They only have mass in one dimension, the dimension they're moving at, and they cannot be moved perpendicular. They can only move in this direction. They cannot move this way or this way.
Its spin, its electron number, and so on. And that always remains. So if a particle comes along and hits something, that is always conserved, and this quantity remains the same.
Right, the conservation, exactly. It's just, the wave part is just completely irrelevant. There's no wave, there's frequency, and frequency is, there's lots of ways to realize it, but the simplest argument, I'll make just a quick one. If I was to represent an electron as this kind of thing, it has arrows going this way, this way, this way, and this way. And so just think of that in all directions. And I add 2 arrows this way. So 1 arrow and then a second one for a photon. So there's 2 of the right polarizations are going to hit this thing. Then it can release. So it's going to gain a new arrows going this way. So it's gaining this and this from that interaction. And what it's going to do is it's going to release this and this. So that's how electrons can release paired photons. Is that if it releases one this way, it has to release the opposite one in the opposite direction. That's one of the rules. And that's EMF for accelerating electrons. But you can understand that as it lets go of this stuff going this way, it's gaining more stuff going this way, which means it'll gain velocity. Not too complicated.
But when it hits things, it does so as a wave, scattering off things as though it were a wave. So all the time it has these two elusive characters going on. And
now, the elusive character is the wave character, because there's absolutely no evidence that photons are ever waving in any kind of material way. It's only in this made-up causal explanation that there's any wave function. There's no material representation of a wave function anywhere in known physics.
I don't know. Physics, when you're 18, is based on common sense, but when you've gone through all this, somehow you get used to it. You don't actually like it. You just get used to it and learn to live with it.
Right. So this is what Pirro would go. I'm the street physicist, and this is the way professionals deal with a problem, is they just pretend it doesn't exist. The problem is this doesn't make a lot of sense. It's all mushy and vaporous. It's, yes, we're going to actually put the Invisible Man on the stand, okay, who has a non-audible voice, and we're going to solicit testimony from him. And as a lawyer, you're saying, why are we doing this? This is a farce. And the judge just says, just do the routine, okay? We like the routine. Just be part of the club. And so Pirro says, because I find fault with this attitude, that I'm saying this is a conspiracy. These people are all liars. They're covering up the truth. And I'm just saying the cover-up is no deeper than this man's frustration, where he's saying, I don't like it, but this is the story we're telling, and until somebody comes up with a better story, I'm going to tell this story. And let's say somebody comes up in my earshot with a better story, because I'm not going to really be listening, because I'm not looking for a better story. So that's part of the problem too. They're really not looking. Feynman and Einstein told them basically that I'm really smart, and if I can't figure it out, you can't. So they all kind of gave up.
That's the language.
I mean, it's an attitude that exists. There's another physicist at MIT who basically says, look, you can't find the hidden variable. You can't find it. We can't find it. We looked, and we're looking, and we're looking, and we're looking, and we can't find any of these hidden variables. So there's nothing to account for this wacky behavior, because there can't possibly be anything we haven't considered. Just it is possible there's things you haven't considered.
That seems to fit.
Alright, some more of the drama. Doopily Dumpily walks to the science lab. Alright, so here's the electron experiment.
What I'd like to see would be a random sort of splurge of electrons. That's not what we see.
Right, okay, so in this experiment what they're doing is they're shooting electrons at matter, and then they're seeing the electrons that bounce off. And the point is they're coming back in specific locations. So instead of coming back in all kinds of random ways, they shoot them in random ways, like in any kind of spot, and they all come back at specific locations. Now, my argument to that would be is that what's happening is the electrons are going into the matter. They're not bouncing off of it, and they're U-turning. And the point is they always will U-turn to the center. So no matter where they go in, they come out the center, so to speak, because the matter itself has a geometry, and that geometry will always force the electron back out from the same location. So the admitting point of the electron has always got a center of gravity, so to speak. There's a center of gravity in the local domains of the material structure, and those local domains will force, like magnetism going out the north end. The force comes in any part of the magnet and it goes out the one end, kind of a thing. And the same thing is happening to the electrons. They come in from any place and they come out from the center, so to speak, from a center.
They are very, very well defined peaks.
Right, so that just explains this pattern, is that the geometry is set by the matter itself, and the point is the admission points on the matter are specifically are requirements. And everything that's really changing is as the electron goes in deeper, it gets bent, and then it comes back out straight. That kind of effect is happening. So as it goes in, it gets bent to the centers inside the geometry of the the matter, and eventually it U-turns and is emitted as a new electron out of the substance. Pretty much. Let's see if there's anything else in here conclusion-wise.
Where the wavelength of the electrons is so much smaller.
Okay, so they talk about the wavelength of an electron. Electrons don't have a wavelength. And the way they make a wavelength for electrons to use it in the math is they just change the velocity of them. So they change the voltage. The higher the voltage, the faster the electrons will fly. And so they're changing the momentum. So you can imagine that if I did do a magnet experiment where I shot magnets through a slit, the faster I shoot the magnets, the less they'll diffract. The slower I shoot them, the more eccentric the bending. So that's the frequency element, why it's important. You have to have a certain wavelength of electron, or the electrons will just shoot right through the experiment, so to speak.
Is we're actually using the atoms at the surface to diffract the electrons.
Right, so that was the giveaway. We're using atoms to reflect them. It says diffract, but you're really reflecting them.
One of the things which I think perhaps students find particularly difficult is that when you're treating the electron as a wave, you can't...
Now, see again, does the electron have a Huygens wave in front of it like the photon has? And then does the buckyball have a Huygens wave in front of it like the other two? I mean, once you start making up these stories about how things get bent, then there has to be some consistency somewhere. Somewhere you have to be obligated to explain how these imaginary wave functions appear, how they're created by these very different pieces of elemental particles. You're putting different collections of elemental particles together, and you're saying they're all creating the same mechanism. Where my argument is no, the mechanism is in the matter. The mechanism is in the fields around the slits. That's where the mechanism is that's causing the change in the direction of the photon or the electron. The field energy is doing it, not the energy of the electron.
Really talk about it being there or there or there, because a wave is everywhere in the volume that you're considering. And therefore, the idea that everything is very delocalized is difficult for people to understand.
Well, it's impossible, I think, to rationally reconcile it with the observed facts and with a consistent model of where you apply principles consistently. So, yeah, it creates huge paradoxes that you all seem to be just stepping right the hell over.
Back in 1923, there was a piece of kit who resembled this that actually gave us really the fundamental proof that electrons had wave-like character.
Right, so they're saying it's proof. They just keep, it's fundamentally proven. We've done it. We finished it. Our assumptions are correct. In my opinion, just really, again, this is the professional science. And in my opinion, that's very unprofessional. It lacks detail and scrutiny. These people are wanting there to be a truth. They're not proving a truth. All right, I don't know who... Oh, Khan Academy. So this is another one where we have no acknowledgement of Huygens. So when he does...
Young's double slit experiment.
So when he does single slit diffraction, he uses Huygens. When he does double slit, you'll see no Huygens.
Looked a little something like this. You've got a barrier with two holes in it, but these holes are so...
So
to be comparable.
This is wavelength
here. It doesn't have to be the same size or smaller, but it has to be...
So this is where he's talking about the wavelength should be the same distance as the impediment. I think that's more relevant to the size of the openings, actually, but regardless. And that's just a convenience, right? Because if you make it like a wavelength and a half, the experiment gets kind of funny mathematically, because now you can't use the same tricks. You don't have a consistent number of diffraction points, so you end up with a remainder, so to speak. Half a wavelengths and quarter of wavelengths ending up over in the math. So they always like mathematically to have the same numbers because that makes the math work better. It has nothing to do with whether you get more pattern. You'll actually get more pattern, and a harder and clearer pattern if you narrow the slit. If you make this opening smaller than the wavelength, you'll get a stronger pattern. No, if you make it bigger, you'll get a more bars.
Around, it can't be a trillion times bigger than the wavelength of this laser light.
Well, no one's talking about a trillion times. We're talking about a half times. So let's go ahead a little bit. He still hasn't gotten through the slit yet.
This part hits that barrier, doesn't get through. This part hits the barrier, doesn't get through. The only portion that's going to get through is basically this portion here and this portion here.
Right. Well, we know that when these are regular tawns, that the same principle applies. Obviously, most of the light doesn't get through the slits.
These are going to be the ones that make it through. And so what happens? What do you see on the wall over here? If this was a screen that you could project the light on, what would you see? Well, naively, what I would have thought, I'd been like, okay, shoot, light comes through here, bright spot. Light.
Okay, so naively, he's kind of almost conceding the point that this is the naive, traditionally vacuous. Let's ignore Newton, let's ignore what we already know, especially now. Like I said, maybe 100 years ago, people not understanding single slit diffraction might have been a sellable argument. They overlooked it. But, I mean, it's not really overlookable now. So why would you, if you know anything about small apertures, you have no expectation that the light goes through and ends up straight over here. You have every expectation that you'll get a diffraction pattern.
Comes through here, bright spot. You just get two bright spots, right? Well, no, that's not what you get. That's why this experiment is interesting.
See, so he's saying this experiment is interesting. He's not saying that small aperture experiments are interesting. He's saying this experiment is interesting. And again, is this being true to the facts? Is this being an honest way to present the physics? This is the foundational experiment in quantum mechanics, in the theory of quantum mechanics, and this is the lack of detail. They have just no regard for the truth whatsoever, in my opinion. I mean, it's like I said, the guy has done videos on single slit diffraction. So how can he possibly, I would imagine he didn't find out just yesterday about it, or he didn't find out after he made this video. So he's just so used to this way of selling it that that's all they're doing. They're just selling the idea by lying to people, by saying, look, you would just expect a little clump here. When since Newton, they knew you wouldn't expect a clump there. You would expect a ring.
Because you don't just get two bright spots. You get a pattern over here because waves don't just travel straight through this hole.
Does this,
when a wave goes a valley over a valley,
so
every time
a long explanation of the nature of interference, but again, this is all based on these assumptions. So no talk of Huygens, two clear waves created and two waves interfering with each other. No millions of wavelets, no, again, the principle isn't applied. The Huygens principle isn't applied. Why the inconsistency? If it's Huygens in the single slit, why isn't it Huygens in the double slit? These are legitimate questions. Again, all this, look, see where they intersect, and it's constructive and it's destructive, and you have bright spot and you have dead spot. All this conversation based on a false premise. And again, no evidence of Huygens.
That's why we do it double slit like this. That's why we take one wave. We let one wave come through here. That way, we break it up into...
That's why you have the same, they're in phase to start with, which is helpful. So again, but this doesn't demonstrate any of the traditional double slit experiment isn't peak, peak, peak. It's bars, and so they always they want to keep making it into a wave. It's clearly a bar pattern. Okay, let's go back to this description. Where's the waviness in this? These are distinct hard lines. There's hard dark spots in between the bright spots. So again, they just want to make it into a wave. They want to, any opportunity they have to wave everything out, they're going to wave everything out. But that's not how the pattern in its clearest form, there's no waves. And this really happens when you take a diffraction gradient which are a bunch of little lines close together, you get very distinct spots where there's light and very huge spaces of black. There's no wave evident there at all. There's a peak, and then a dead long black spot, and then a little peak, and a dead long back spot. It's clearly a frequency, not a wave.
Two pieces. Why? Because we know if a peak was going into the top hole, well, the same wave was going into the bottom hole. That's also a peak. This is a tricky wave because zero gives you a constructive point.
Right. So this is where I was talking about the fact that when you draw it, it's it's an illusion that these two spots are really huge and this target is very small. And so none of this would ever happen because this space is a nanometer across and this space is meters long. So there would be no effect like this. This would be irrelevant to any kind of image projection, just because this is so massive compared to the size of this tiny, tiny, tiny emitting spot. The emitting spot is so small. So it's another. Don't pay attention to the reality. Pay attention to a drawing, and the drawing just isn't good enough representation because he didn't say that explicitly. That there's no point in talking about any of the light inside of this bright spot because all the light not diffracted or interfered with is going to end up right here. Because this is a tiny, tiny, tiny spot by comparison. So, but anyway, so it requires some significant diffraction for the signal to reach these points. Alright, so this is probably enough. But again, no Huygens, double slit, no Huygens mentioned whatsoever. That's Khan Academy. This is a teaching institution financed by Bill Gates' big money, and they can't even get it right. So I don't know, I don't think I'll bother with the uncertainty principle. And I am getting a little tired, so I think that's enough. So I'm just making the argument that this is done so poorly, and it is so unwell evidenced, that there's plenty of room for conversations about alternative theories that are causing the photons to be changed in their vector of momentum. And the fact that they've closed those conversations and are just obnoxiously and arrogantly stating this is the most proven theory and the most proven math, and yet the math doesn't produce the shape that really exists. They don't spend any time detailing these bars and the number of them. There's no chart of two-slit experiment where you get a nice detailed chart of exactly, like, I changed these razor blades and I changed the effect, and they count the number of bars for how much they move. There's no detailing of what changes in the experiment create what kind of changes in the result. There's not one source you can go to where you get to see exactly what changes create what changes. And if there are any, they're synthetic projections of the math, not projections of reality. So that's another thing I could show you, is there's a couple of simulators that are math-based, and they don't produce real results. They produce these mathematical results that are sanitized out of this reality. Alright, so that's enough. So, till the next time. But I just find it really obnoxious for me to be ridiculed as a hack and an amateur and a slob and a bum scientist, when the high-paid, highest quality, most authoritative professionals make such glaring misrepresentations of the truth. It's really disgusting for people to call me the incredible shit talker when there's such glaring evidence of who's talking shit about physics. Enough said.